magnetic force on a current carrying wire. Let's look at a current carrying wire. Okay, it's in the middle of a magnetic field. In our case, the magnetic field is towards you, perpendicular to the page. A magnetic field exerts a sideways force on moving electrons in the wire. This force must be transmitted to the wire itself because the conduction electrons cannot escape sideways out of the wire. For example, if the currents go this way, you have the I cross B is 12. If you change the direction of the current, the force will be different. Now, let's calculate how much force acting on this wire. Okay.
We'll use a large horseshoe magnet and a current-carrying wire to show the force a magnetic field exerts on a current. The wire is placed between the arms of the horseshoe magnet. Then 20 amps is run through the wire in the direction shown by the arrow. The wire jumps out of the magnet. This diagram shows the directions of the current, the magnetic field, and the force on the wire as predicted by the right-hand rule. If we reverse the magnet and run the same current through the wire, what will the wire do? This time the wire doesn't leap out. The magnetic force on the current now pushes the wire down.
Now let's calculate. How many force acting on the wire which carrying I? Suppose this is section of L. Now we see the force acting on this section is actually the force acting on all the conducting carriers in this section. Now let's calculate the force, magnetic force, acting on the section L of this current carrying wire. Of course, this is the sum of the forces acting on the charge carrier in this section. Then we count how many charge carrier in this section. Now, this is the currents going up. That means the electron move down. And we started from here. Okay, how much time it need to cover air? That is, okay, this is each force on each carrier electron. Okay, and then it takes time t. T is air over VC. This time it's from here to here, and all these carrier is in this air. How many? Before we calculate, we can the t. The t is air over v piece, and the q. What is q? Q is the it. This is current intensity times the period, and the period this one. So in time t, you have all these q flow into this section, and the force, the total force acting on this carrier, is the force acting on this section of air. That's character. Okay, so the FB for each one is QB, QVB. This is sine 90 in our case. The V is the direction, the B is perpendicular to the page towards you. So FB equal to Q. Q is IV over L times VB, and V cancel out equal to ILB. This equation gives the force that acts on the segment of a straight wire of length L, carrying a current I, and immersed in a magnetic field B that is perpendicular to the wire. And we can write, in general, we can write this, we can write DB equal to IL cross B. That includes the direction, okay? You compare this one, this is on a charge Q, this is on the current IL. FB equal to IL cross B. This is IL, okay? This is B. The angle is phi. So this is, we use right hand rule, IL cross B. You get this direction. Perpendicular to B, perpendicular to I, okay? And we compare with the charge. And it's similar, very similar. This is a charge velocity, this is a current length. Rewrite it, okay? The phi b is the angle between them. Okay. If a wire is not straight, we can imagine it broken up into a small straight segment and apply for each straight segment IDB equal to IDL cross B to each segment. The force on the wire as a whole is then the vector sum of all the forces on the segment that makes it up. So you do the integration, you get FB equal to integration DFB equal to integration IL plus B. Don't think that's simple. It looks simple, but when you do it, it's not simple. This is a vector. You have to dissolve into x, y, z direction. You find FBX, FBY, FBZ, respectively. And then you combine these three components, FB equal to FBXI plus FBYJ plus FBZK.
This light bulb is attached to a two-way switch so that it can be powered either by direct current or alternating current. When we bring a large magnet up to the light bulb when it is operating on direct current, the filament bends to one side because of the magnetic force on the electrons flowing through the filament. If we run the bulb on alternating current instead, the filament sways back and forth 60 times per second as the current reverses direction. We'll use this aluminum disc, which spins freely between the poles of a horseshoe magnet, to demonstrate the force that acts on a current flowing in a magnetic field. Two pools of mercury electrically contact the center and the bottom edge of the disc. When a large current flows between the center and the bottom of the disc, a magnetic force on the current pushes the wheel to one side and starts it spinning. Reversing the direction of the current reverses the direction of spin. This glass dish contains a solution of copper sulfate between two copper rings. A magnet in the center ring provides a magnetic field which is pointing vertically upward. When a current is run between the copper rings, magnetic forces on the moving ions produce a sideways force that spins the copper sulfate solution, as shown by small pieces of cork floating on top. Reversing the direction of the current reverses the motion of the solution. Reversing the magnet reverses the spin. If we remove the magnet from the center of the dish, the spinning soon stops.
Sample. A straight horizontal length of the copper wire has a current I 28 ampere is towards you, the I. What are the magnitude and the direction of the minimum magnetic field B needed to suspend the wire? That is, to balance the gravitational force on it. The linear density mass per unit length of the wire is 46.6 grams per meter. Now, the key point is what to balance it. So the FB must be upward balanced as well. So the magnitude it must be equal to mg. In other words, mg equal to ILB sine phi. Phi is the angle between B and the current. We don't know. And in order to find the minimum B, we must have the maximum sine phi. In that case, phi is equal to 90 degrees. Okay, so B can be minimal. And this is a 1. In other words, the angle between B and A is 90 degrees. So is the direction perpendicular at perpendicular to 1, okay? And perpendicular to I. Then, very simple, B equal to mg over IL. And L over, let me see, this is ML. ML is 46.6. Remember, we have to use the unit kilogram. So we must 10 to the minus 3. Okay, and we get the answer.